Okay. Well, everybody, this is yet another instance of the MSE 403 1003 lecture series, tied to our self-driving labs class. Today, I'm very happy to have Professor Kris Reyes from the University of Buffalo coming to speak to us. Um, Kris is one of the people that I go to when I have questions about Bayesian optimization and the design of policies. He is absolutely one of the strongest leaders in our field. He's been working
Yes.
at this for a number of years, thinking really hard about not just can I use a GPR to do Bayesian optimization? But even starting to think about the meta questions about how do I optimize the optimizer? How do I define an optimal policy when I live in a world where I don't know what the true answer is? Um, Very mathematical in his approach to these types of tools, and frankly, quite creative. And so, Professor Reyes, again, as always, I'm looking forward to your presentation. And please, with all, floor is yours.
Sure, thank you. And I'm very excited to come talk because I think this class it's a very unique class, and you should not take it for granted. I think what you guys have the opportunity to learn is a very unique thing and a very important thing to learn. And so I'm very happy to come chat. And so what I wanted to talk to you today is about Bayesian optimization, but really about thinking about how do you know whether or not your Bayesian optimization campaign was successful? Because this turns out to be a more difficult question to answer than most people, I think, really appreciate. So, what do I mean by Bayesian optimization? So, I appreciate you just kind of started the semester, and so you are probably just starting now to talk about this. But let's remember what the setting that we're in. We are building a self-driving lab, and in our self-driving lab, we're trying to explore some sort of recipe space or like a synthesis space. I sit inside a material science department, so I'll talk in terms of materials. But the idea is that you're trying to explore some sort of recipe space, and you have a goal in mind. What you're trying to do is you're trying to optimize. So you have your recipe, you synthesize your material, or you fabricate your device, and then you measure some property of that material. And what you're trying to do in, say, the optimization setting is to find where that property is maximum, for example, with respect to your synthesis recipe. You're trying to find what's my best synthesis recipe that like maximizes, in this case, um, like the yield or the length of the carbon nanotubes we're trying to grow. Um, and so we could approach this problem in lots of different ways. And I think one of the um, more popular ways to do this in the SDL space is this notion of Bayesian optimization. So, what is Bayesian optimization again? So, it's this idea that we're going to explore the space one by one recipe at a time. And the advantage of doing that is that we could take the outputs of our experiments one by one and use that as in like a feedback loop to inform what other experiments we're going to do in the future. And so there's really two ingredients to this. And you've been starting, apparently, you've been learning these ingredients. The first thing is what we call a belief model or a surrogate model. And really, what this is supposed to say is what is our prediction of the relationship between our inputs, say synthesis temperature, and our outputs? And we're going to do this in a Bayesian manner. So this is the Bayesian part of Bayesian optimization, which means that we're going to take our data and we're going to do like, you could try to imagine fitting like some sort of regression model to kind of fit the existing data that we have and that we're growing in our campaign. But then the Bayesian part is that we're going to perform a sort of uncertainty quantification, right? We're going to be able to say, yeah, I believe my response function, the function of the property that I'm trying to optimize with respect to my recipe, on average looks like this blue line. But this blue line is based on a very, very small set of data. It's like 4 data points. And we know that that's not going to be accurate. Like it's a tiny data set size. So let's be honest with ourselves and say, well, there's actually a lot of uncertainty involved in these predictions. And so you can kind of codify some notion of uncertainty on these predictions. And I think one of the popular models to do this, which you've learned about, is something like a Gaussian process, right? So you see these types of plots in a Gaussian, whenever you're studying Gaussian processes, these so-called like football plots. Okay, so that's the key ingredient. The belief model, the surrogate model that encodes our estimate of our response and also our uncertainty on that estimate. And then what we do is we take this belief, uncertainties and all, and we feed it inside a decision-making policy. And the decision-making policy is responsible for saying, you should run this experiment. And a good policy, because we have these uncertainties, doesn't just look at the blue line and says, well, if I'm trying to maximize carbon nanotube length, I should do this recipe, the one that corresponds to this one, because my estimate says this is the best. Because we have to take all of these estimates with a grain of salt. There's uncertainties to this. For example, over here, we have regions with large uncertainty. And so you can imagine a decision-making policy to say, well, let's do experiments here because we have large uncertainties. Getting data here would reduce those uncertainties. But in this region, if we're overall concerned with optimizing, say, maximizing carbon nanotube length, a good policy wouldn't pick this region either because it's very unlikely that any data points in this region would be large, like compared to what we sort of already know. The decision policy is always trying to balance between experiments or recipes that we estimate to perform really well and experiments or recipes that we don't really have a good understanding of the resulting outcome or the property, right? And that tension is called the exploration versus exploitation dilemma. And a good policy doesn't pick either of the extreme, doesn't say do this one because we predict it to be well, or do this experiment because there's a lot of uncertainty, but it usually picks something in the middle. An experiment that, according to our model, um, is decently performing, but there's still uncertainty, so there'd be value for running that experiment. So I'd probably pick something over here because there's a high likelihood that it's bigger than our data because there is still uncertainty here. Okay, so a policy picks that. We feed this to our robot. The robot runs that experiment. It performs the characterization to measure a property. It gets a new data point in our data set, and we update our model using Bayes' law essentially to get us an updated set of beliefs. So this would change if we get a new data point. Okay. Moral of the story: two ingredients, the model and the policy. The model can be used, for example, to estimate where we think experiments are good and uncertain. The policy is going to pick between the two. Okay. All right. So you run your campaign, and what you do is you're measuring your response that you see at each step, right? You repeat this like 20 times, and what you get is a choice of an experiment and the resulting response that you observe. And then a lot of times, if you were to plot this is in practice. Ignore the dotted line. You get plots that look like this, right? Where again, you're trying to find the synthesis recipe that maximizes your response, and then you get this, and you sort of sit and stare, and you kind of are asking yourself, well, this is supposed to be an optimization. I'm trying to find my recipe that optimizes my response. What's happening here? Um, is this a good outcome or not? Because like maybe like eventually like you could say, well, like after 26 experiments, we considered a recipe that gave us a pretty high response. And maybe this is good for our system. But then like it's kind of like it's jiggling all over the place, and it kind of went like far away, and then started performing really poorly. And there's no sense of convergence. Like maybe you're more familiar with machine learning, and you keep track of these during training of a machine learning model. You sort of look at the loss function as it decreases, and it's really really nice because you kind of see the loss function decrease and kind of stabilize to and converge to a low value, which means you've kind of properly trained your model. And so maybe you're expecting that type of behavior with this type of plot. Most people do. Um, and unfortunately, this is the problem here is that this plot in our setting for Bayesian optimization is very, very misleading. And you actually can't get a lot of information by looking at this plot. We call this the observed response versus the number of experiments. Nevertheless, you could kind of, after your experiment, your campaign, you've done 60 experiments or whatever, you could look at this plot and you could say, well, we got a good result. Was this a fluke? If I were to repeat this again, this looks kind of random. Is this going to happen again? Like, did I just kind of run into this good recipe just by accident? And then you could ask, well, how do I measure whether or not this was good? Like, we can't really say anything about convergence. Maybe like we could say something about the maximum response we've seen so far, but like we kind of veered away from that. So what is the proper metric to use to answer the question of whether this was a good campaign? And you may be also be what we call prospective, right? You may be like in the middle of your campaign or at the start of your campaign, and you could again try to ask the question of, well, given everything that I've put into my modeling and my policy, do I think this is going to be a successful campaign? How many
Oh, but
experiments should I run? Yeah, go ahead.
I'm sorry. I moved a podium and pinched my.
Okay,
Keep going, Kris. It's okay.
yeah. You could ask, how many experiments should I do? Should I do 20 experiments, 50 experiments, 100? What's a good sort of budget to allocate? And what policy should I pick, right? So there is not just one way to balance between exploration and exploitation. There's actually lots of different ways. And so the question is, which one should I do for this experiment? Okay. And the main message here is that this is all a question about performance, either past performance or predicted future performance. And this performance is measured by metrics. That's the definition of what metrics is, and right. And so the metrics that we use to assess performance really depend on what we're trying to achieve in our closed loop campaign. All right, so it depends on our task. So let's be really, really specific about what we're trying to achieve in a Bayesian optimization campaign, right? So in Bayesian optimization, very specific here, what we're doing is we're using a Bayesian model, like the Gaussian process, and a decision-making policy in a sort of iterative or step-by-step process, so that by the end, we've sort of identified the optimal recipes of our response function, right? And that's very important here. The operative word here is by the end of the campaign. And the second operative word is identify. We sort of are able to predict the optimal inputs. Notice I did not say, and this will come up later, I did not say that during the campaign, we need to be able to have a good understanding of the optimal value. And notice I didn't say that we have to actually see that optimal response during my campaign. We just have to, by the end, have a prediction of where the optimal input is. We don't have to do this during the campaign, and we don't have to actually observe anything optimal during the campaign. All right. And so it's very important to be specific about this, because the measures that we use to identify whether or not we've accomplished this are very, very different from the metrics that of fields that Bayesian optimization draws from. So Bayesian optimization is sort of this combination between Bayesian statistics, machine learning, just classical optimization, experimental design, and reinforcement learning um, ideas. And all of these fields, yes, we're drawing from them, but they all have different tasks that are different from Bayesian optimization. And so that leads to people who are more familiar with these other fields and are going into Bayesian optimization. They sort of carry that baggage along with them to say, I know from machine learning, I care about accuracy of my model. Maybe that's what I care about in Bayesian optimization. And the answer is the correct way of thinking specifically for that is no, you don't care about accuracy of your model. And people hear this and it sounds blasphemous, but no, you act like that's just one example. So let's be specific about this. Machine learning, what is the task of machine learning? You're going to have data, and what you're trying to do is you're trying to train a model so that based off of that data, you can kind of predict values of that response in places where you've not seen data. You want to be sort of globally accurate, or you want to be generalizable. Right? You want to have a model that can make accurate predictions. So in that setting, where you care about accuracy of your model, well, that's your metric, right? You just want to be able to say, for example, what is my accuracy of my model in predicting outputs? Sorry, I don't know why. On a test data set or like a holdout data set. Okay. Um, and then that's measured by whatever accuracy. If you're doing classification, like precision and recall, things like that. Again, contrast this with what I said earlier with Bayesian optimization. That the task in Bayesian optimization is not to train a globally accurate response model. The task, again, is to identify by the end of your campaign where the maximum of your response function is. Okay, and here's just an illustration of this. Here is sort of the ground truth that we don't know, this red plot. The black plots here are maybe data points that we measured. And this blue plot here sort of shows a fitted model to this. And if you were to give this to a machine learner, they would say this model is very, very crappy. Like this is not a good model. It doesn't predict the red plot at all. But then, and which is true. This is not a good machine learning model. But this is a great model for optimization. Why is that? If you look at where this model says is the best input, and you actually look at what the ground truth is for that input, this value, I mean, it's not the best, it's not the optimal response, but it's a pretty good response. So for 3 data points, identifying a decently performing input is a great result. And if you compare this with the actual true best, you can compare these two. And this is just another metric that we call the opportunity cost that compares the actual true best value versus the true value at what you think is the best. And we want this to be small. And so this is, again, an illustration of why global accuracy is not the goal in an optimization problem. Again, another field from which we draw on is optimization, is in particular gradient-based optimization, or what I'll call model-free optimization. And in gradient-based optimization, maybe you've heard words like gradient descent, stochastic gradient descent, atom. What those types of optimizers do is that they're sort of an exploration of the landscape. So you start off at one point, and then you use local information about your response function at that point to decide, oh, this looks like it's sloping upward. I want to have around this area, this looks like my ground truth is sloping upward. I want to go up, so let's just follow that direction. So I'll go here, and then I'll go here, then I'll go here, and all the way up to the top of the hill. So it's a hill climbing algorithm. And this is model free because the only information about our response function that we keep around is what we know locally when we evaluate that function at these points. So you only care about when you're making a decision of what experiment to do next, all you care about is the slope of this function and where that slope is pointing upwards. And you just sort of go in that direction. And so in that sense, your gradient-based optimization, you kind of have to, because you're not holding extra information around in a model, you kind of have to hope that you visited along your journey, along this hill climb, a good value because you don't hold any other information about your truth. The only information are the data that you actually see in the in your hill climb. Contrast this with Bayesian optimization. Bayesian optimization, like we said, is model based. We have an underlying model of the entire ground truth all over the place, not just at the data points that we have available to us. So we have a model of the entire landscape, which means that we could actually predict where the maximum is or have a prediction of where the optimal value is without having data points at that position, right? For example, we have 3 data points here, 1, 2, 3, the black. We fit in a model, and the maximum value predicted by the model is right here, which again is pretty decent, actually pretty decent with respect to the truth. But this input was never visited in our 3 data points that we based this model off of. So we don't need to visit a maximum response in order to predict that the response is maximum there. Okay? So these two observations kind of tell us why, like, our intuition based can often, based off of like machine learning or optimization, can often lead us astray when we're trying to assess whether or not we've achieved the goal of Bayesian optimization. So let's make this clear. Here is our belief. So we're running our experiment. We have some sort of belief about our response function. Let's be clear. We have what the model thinks is the best experiment, right? This is a choice of the model. And we have what the policy thinks is a good balance between exploration and exploitation. And these two experiments are not the same. We have a choice by the model and we have a choice by the policy. And these things are picking 2 different things based off of their goals, right? And so that leads to a few key observations. Number 1A, this model could probably estimate what the best experiment is, but we're not going to pick that experiment in our Bayesian optimization campaign. We will not pick this experiment ever. We will pick this experiment. So the experiments that we pick in our Bayesian optimization campaign and the responses that we see for those experiments are never going to be what the model actually thinks is optimal. So underlying throughout our campaign, we have an idea of what's a good experiment, but we're never trying that in our campaign. So the responses that we see, we know aren't going to be that great. They're not selected to be great. They're selected to balance between exploration and exploitation, right? In particular, the prediction of the best doesn't have to be in any experiment that we selected during the campaign. Because again, we're picking experiments that are not best according to the model. We're picking experiments that balance between exploration and exploitation. Another key point here is that our policy, because we're trying to put in a type of exploration, we know that the experiments our policy picks, our model is uncertain about the values. So what does that result in? We know that before even running this experiment that the policy picks, that our prediction is wrong. That's the whole point. Like we know there's uncertainty with this prediction. That's one of the reasons why we picked it. So we know that we don't have to, the prediction may be wrong. Okay? And then the last point here, and just to build off of that, is that if your Bayesian optimization is working, if your policy is actually trying to identify the best input by balancing between exploration and exploitation, even by the end, after a reasonable number of experiments, say 50 experiments, you're still going to have these large regions of uncertainty. And that's the point of Bayesian optimization. And at the end of your campaign, you are not going to have a globally accurate model. You are going to be avoiding these regions because there's very low probability that this is going to be optimal. So you'll have large regions that remain uncertain. There's a question. Let me read it. It's because it's kind of long. From the description of the difference between Bayesian optimization and machine learning, does it mean that with Bayesian optimization, it could tell us about the input that maximizes the response, but it might not tell us value of the response accurately? So we shouldn't rely. Yes, yes, that's true. That's another setting. It won't actually. We don't actually need to predict the value correctly. We just need to be able to predict that it is a good experiment. Right? It can be off by an order of magnitude, and that's still fine, which is not acceptable in machine learning. Like, so you could totally have a model that says this is a good recipe. This is a good recipe, and that can be correct with respect to the ground truth, but the actual prediction of the response could be totally off. So yes, all you have to be able to do is predict the location of the maxima and minima, not necessarily their value. That's a great point. Okay, so what, again, to reiterate, is the objective of model-based optimization? And it's this. So the goal is to ask how efficiently along at each step of our campaign can we effectively identify the optimal value or the near optimal responses? How effectively does our model, because our model is changing. So we're always updating our belief about where the best experiment is. But how quickly can we identify that best experiment, right? And the point is that in these key points sort of lead to incorrect metrics that don't answer this question. And the unfortunate part is that these metrics are kind of prevalent in the SDL literature. And so one of the reasons why I'm talking so passionately about this is because I'm sort of on a personal mission to stop the spread of these bad metrics. All right. So for example, key point 1A, the model can estimate what's best, but we're not going to see those choices of experiment during the campaign. So what does that mean? That means an incorrect metric is this plot of the responses that you see during the campaign as a function of number of experiments. I showed an example of that plot in the beginning. Just the responses seen during the campaign. And this plot is all over the place. And it's unfortunate because I think people are trying to make this plot look like it's converging. And when they see that it's jumping all over the place, people will jump through hoops to kind of justify it or hide the fact or something like that. And they do expend so much effort trying to make this plot look closer to their intuition. And that's just wasted effort because this is not at all the metrics that you want to measure in trying to answer this question of whether we've achieved our optimization goal. Key point 1B, we don't actually have to visit the best input during our campaign to predict that it's best. So even these plots, you kind of see one way to correct this plot is they kind of draw a line between like the record breakers. What's the best response that's seen so far? And that remains constant until we sort of find a response that's better than that, then that sort of jumps up. So you sort of see this envelope of like the best response seen so far. And again, that's slightly better, but there's no guarantee. We're not going to be visiting what the model thinks is the best. Like we actually are probably able to estimate our good inputs, but not actually see it in our campaign. 2A, the model is going to pick an experiment with uncertainty to response. So we know in advance that our prediction is wrong. So you see this as well. Like this, especially people coming from machine learning, they will try to kind of say, okay, let's measure my policy says pick this experiment. Let's measure how accurate the model predicts the outcome will be versus what we actually get. So the accuracy of the prediction before running an experiment. And again, accuracy is not the metric to even consider when we're talking about optimization. Um, I mean, at least to first order. And then overall, we're at the by the end, we're always going to have large regions of uncertainty. There's going to be our model is not globally accurate. So testing the effectiveness of your model on a holdout or test data set, again, it is not that important because if your Bayesian optimization is working, then you don't have a globally accurate model. We ignore parts where there's a low chance of, we ignore regions where there's a low chance of being successful. Okay? All of these metrics we see in papers all over the place. Um, and it's unfortunate because, again, it's a lot of expended effort trying to make these metrics look consistent with our intuition. But the main point is that our intuition for Bayesian optimization is not correct. It's not the same as our intuition for machine learning or model-free optimization. Okay, Jay asked a question. In class, we will take a somewhat weird view on Bayesian optimization, one that prioritizes best experiments and sometimes that prioritize samples that build general models. Yes, yes. And the point is, a good policy will sort of make that prioritization for you. Like it'll sort of be an emergent property of when it prioritizes building generalizable models to some degree and when it prioritizes picking the best experiments. And at least in the setting of strict Bayesian optimization, a good policy will do that management for you. Okay. And I'll explain what I mean by that if I have time. All right. So um, I don't have time. So what should you do? So let me just conclude with this. Um, so what is the right metric? So the idea here is that, again, at each step of your campaign, you will have a belief about your response function, right? And that belief is going to change. And so what you can do, this is after you've done your campaign, you can go back and look at your data and say, oh, at the first step, my belief was this. After my second step, based off of the data available at the time, my belief looks like that, and so forth. And what you can do is just ask, okay, at the very first step, after that, I predict this input is my best because I'm just looking at my model there. And then at the second step, I think this is my best input. My third step, I think this is my best input, right? So you can kind of retroactively figure out what my beliefs thought were the best inputs, what actually maximize the property that we're interested in maximizing, right? So you have sort of this collection of experiments that we did not run during the actual campaign. The experiments we ran during the campaign were selected by the policy, the balance between exploration and exploitation. These are different experiments. These are what the model thinks is the best at each step. And then what do? You just run these experiments, right? You say, okay, now how good are these predictions of the best? So you'll get responses at these inputs. And this is the plot that you should try to look for convergence and it sort of asymptotically approaching like a good value, right? This plot of the predicted, the ground truth response at your predicted best is what you want to plot. This is what corresponds to those plots of the loss function in machine learning training or any other optimization algorithm you are used to. Okay, this is your performance metrics to judge for optimization. Okay, and I just want to point this out. Um, in order to do this, what you're going to have to do is you're going to have to double your work. You have to need an auxiliary set of experiments that you do at the end of your experiment, a campaign. And so the question is, well, what if you don't want to do that? It's like you're doubling your work. It's too expensive. I don't want to do that. You don't have to run actual more experiments. And so you could imagine an idea here is, well, instead of actually running experiments, let me look at my final model, the model I arrived at the end of my campaign, and use this sort of as a surrogate for running the experiment, right? So you can imagine, okay, well, here's my final model. Here's the input that my first model thought was the best. And instead of running this experiment in a real life experiment. Instead of giving this to your robot, you just evaluate the final model. You're like, okay, this is what my final model says. What we would have gotten if we ran the experiment. So I'll just use that instead of running the experiment. And then since this is sort of like a simulated experiment, and you repeat this throughout for all your other inputs. Okay. And that's sort of an okay idea, except for, again, key point number 2B. If your Bayesian optimization is working, then this final model will have uncertainties here. This is not an globally accurate model. And so, for example, because this is in a region with large uncertainty, this may be inaccurate. So having just your estimate in your final model as your surrogate to running experiments is not the right thing to do. And unfortunately, I don't have time for this, but what you really should think about this final belief is not giving you a single surrogate of the ground truth, but you actually have an entire distribution of surrogates, right? And so you're not just for any choice of experiment getting one value of what the experiment, what the robot would have reported back to you as a surrogate. You actually say, for a single experiment, you'll have a whole bunch of possible values. And so what you get is a distribution of surrogates, and therefore you have a distribution of simulated responses. And in fact, what you'll get is a distribution of performance plots. And so what you'll see are plots, what you should be plotting if you're going to do this final belief as a proxy for running experiments, is actually a whole distribution of this simulated best response, these Y star I's over experiment numbers. And you don't have a single plot of these, you have several of them. And then you can kind of estimate like summary statistics of this. So you have a distribution of performance plots. So you could say, okay, well, on average, I get this. And then you could talk about like variances as well for spread. Okay. And in that setting, that's sort of the best that we could hope for in the setting where we have lots of uncertainty of my response function, right? As Bayesians, we're sort of characterizing not just a single performance plot, but a whole distribution of performance plots. Okay. And then you can use, so I'll skip here just so we have time for questions, but you can extend this idea of using your belief as of having a distribution of surrogates to make these performance plots to actually predict future performance of your campaign. And then what you end up doing, I'll skip this, is getting plots like this, where you're saying, well, if I were to run, 60 more additional experiments with different policies, instead of actually running those experiments in real life, I could simulate running these experiments. And you could use this to, for example, select what policies to actually implement. And so you end up with plots like this. These are called the OC plots, like the opportunity cost plots, but lower is better. And what it shows you is the result of these performance metrics for future experiments, where we're simulating the responses by sampling from our final belief, from our model. We're sampling response values from our model. And what this is showing you is 4 different policies. And it's kind of telling you that this blue policy, the EI policy, is kind of the best with respect to minimizing your performance metric that you're trying to minimize. Okay, so I'll leave it at that. So here are my key points. I'll leave it up here. Sorry to leave 1 minute for questions. I'm very happy to answer any questions now or via email. But the moral of the story here is that you really have to leave your intuition about machine learning and classical optimization out the door when you're trying to assess your performance of Bayesian optimization. All right, thank you.
All right. So